A processor like this Intel 8085 is a physical device. It responds exclusively to two electrical states, a high voltage or a low voltage. To process information, the 8085 relies on an 8-bit data bus. Data flows through 8 physical pins, moving as continuous pulses of ones and zeros. Humans communicate using decimal numbers, alphabets, and abstract logic. Translating that nuanced world into tiny electrical pulses requires a precise bridge. The instruction set serves as that bridge. It acts as the processor's built-in dictionary, a rigid, mathematical grammar that maps our human intent onto specific machine actions. Understanding how computers operate requires learning the exact mechanical language they use to speak. Every command sent to a processor contains 2 parts. First is the opcode, the verb, which tells the chip what task to perform, like adding numbers. Second is the operand, the noun, which is the specific data the verb acts upon. Because the hardware of the 8085 uses an 8-bit architecture, these verbs and nouns conform to hard physical limits. Their size is measured in chunks of 8 bits, known as bytes. This single 8-bit block represents a 1-byte instruction, packing both the verb and implicit target together. When it needs external data, it uses a 2-byte instruction, the verb, then the 8-bit data. Commands locating data in memory need a 3-byte instruction, adding a 16-bit address. The physical dimensions of the microchip dictate the literal length of the sentences in its programming language. We can group these instructions into 5 functional families based on what they actually do. Data transfer commands, like move, are the couriers. They relocate data between registers without altering the information. Arithmetic and logic commands, like add, form the mathematical engine. This is where the actual computation occurs. The results of these calculations trigger a special 5-bit gauge called the flag register. Arithmetic operations flip 1-bit hardware flags, like sign, 0, and carry. If an operation results in 0, that string of 8 zeros triggers the z-bit, flipping it from 0 to 1. Branching instructions, like jump on 0, read these flags to make decisions. The processor checks the status of the flag register, and if the 0 flag is lit, it alters its path and jumps to a new sequence of code. Control instructions, like halt, serve as the overriding commands that dictate the processor's ultimate state of operation. Arithmetic altering hardware flags, combined with branching commands that read them, provides the feedback loop necessary for conditional, autonomous behavior. We have moved past the 40 out of the 8085, scaling up to massive silicon wafers packed with multi-core 64-bit architectures. Speed and memory capacity have increased exponentially, yet the underlying logic remains unchanged. Modern video games and search algorithms still rely on this cycle, opcodes acting on operands, evaluating hardware flags, and branching to new addresses. Decades of engineering built this system, successfully translating abstract mathematical thought into a flawless mechanical grammar. This system relies on a beautifully rigid sequence of syntactic logic, executed billions of times every single second.